Welcome to Part B of ENG 1060. So by now I hope you understand what Part A of this unit was all about. Part A was about how to use the programming language MATLAB. And you did MATLAB basics, matrices, M-files, functions, input, output, nesting, loops, and have some understanding of the limitations of MATLAB. And by now I'm going to assume that you have the basics you need to start programming solutions to real problems. And that's what we're going to be doing in Part B of this unit, actually using MATLAB to look at real type problems. So what's Part B all about? Part B is about using MATLAB, and I am going to assume that you're expert, even though I know that's not really true. You are going to have to sort of pick up your skills. What you're going to do here is you're going to develop these programming skills in far more depth in order to develop the numerical tools that are the tools of the trade for us engineers. And the methods that we're going to learn in this part of the unit are common across all branches of science, engineering, finance, and actually a whole range of other disciplines as well. You are likely to use these in the rest of your degree and potentially for many years afterwards, especially if you move into an engineering career. One question I often get asked by students is, am I ever really going to use MATLAB again? Well, in your degree, I think I can fairly confidently say that most of you will be using MATLAB again. So this is not a unit that you will do and then forget. This is something that you'll have to go back and refresh into the future. Will you use MATLAB in your job? Well, that's perhaps less certain. Maybe there are definitely companies out there that use MATLAB, but not necessarily. But I think as Tony said in Part A of the course, it's quite important to understand that what we're learning here is a way of thinking. It's not just how to use MATLAB. So programming requires you to break a problem down, to understand how the parts work, and then put the parts back together again to solve the problem. This process that we have to use in programming is basically the same process that you need to use to solve very many engineering problems. So even if you never use MATLAB again after leaving Monash, the rigor and the processes you need to help you program are also going to help you problem solve in the future. So this course, the rest of this course is broken up into 5 different topics, and each topic will have 2 different lectures. The first topic is root finding. And so the roots of the equation y equals f of x are the values of x where f is equal to 0. So if we have the curve down in the bottom right, it's our function f of x. The roots of this equation are the x values at which the function is 0. So x is equal to about 0.6 and a little bit over 1.4 in this particular example. So where's root finding practical? Why would we be interested in doing this? Well, it arises all over the place. For example, in sport, intercepting a football or a netball or a basketball can be framed as a root finding problem. So my position minus the position of the ball is equal to 0. In finance, how much can I afford to borrow? It means my income minus the loan repayments minus my other expenses is equal to 0. That will tell me how much money I can afford to borrow. In engineering, it's a very, very common occurrence. For example, the minimum strength of material needed in a particular application. So for example, the structural strength of my structure minus the load that my structure is going to incur needs to be 0. Well, it certainly needs to be bigger than that actually. Otherwise you'd be close to failure. But this tells you what the minimum strength is. The second subject is curve fitting. So finding a function that approximates a set of data. Where might we use this? So for example, in demographics, estimating population trends. If we have some understanding of what the population has been doing over the last little while, we can project into the future. In finance, predicting business revenue based on what's happening in the past and also what's happening, for example, with legislature and indeed in demographics. Importantly, in engineering, we would use it in deriving physical relationships that say how things a function of something else. So for example, what's the force on a building as a function of the wind speed? We do it also in chemical and biological reactions. So estimating the reaction rate in these things, again, usually from experimentally measured data. The third topic is loosely described as integration. And in its simplest form, integration is just the area under a curve. So in practice, integration arises all over the place. So for example, what is the area of that parcel of land bounded by the roads and that river? What is the volume of water in a dam? How can we estimate how much water a dam will hold after we've built it? You need to do integration to do that. And what is the wind force on a building? We need to know that in order to design it so that it's not going to move too much. The fourth topic is ordinary differential equations, or as we will call them, ODEs. Typically, ODEs describe how the rate of change of something depends on other variables, and for a typical first order equation we would write dy dt is equal to some function of y and t. That's a typical first order ordinary differential equation. And so where do these arise in practice? Well, in ecology. So the Lotka-Volterra equations describe the relationship between a predator and prey system. In economics, the Solow-Swan model describes economic growth using an ordinary differential equation. In engineering, a very good example is the simple harmonic oscillator equation. It's actually a second order equation, this one. We have a second derivative on the left-hand side. But these kinds of equations arise everywhere. And the final topic is linear algebra. And linear algebra predominantly revolves around solving a very simple equation. Ax is equal to b, where A is a matrix, x is a vector of unknown quantities, and b is some right-hand side vector. It sounds like it should be simple. It sounds quite dull, but this equation is at the heart of nearly every software product you will use as an engineer. Anything that does anything technical, calculates stresses, strains, anything like that, you'll be solving equations like that inside the program. Linear algebra is actually an enormous field. There are literally thousands of textbooks available out there on linear algebra. It's used in solid mechanics, structural mechanics, fluid mechanics, optimization, and a whole range of other places to boot. So that's the subject matter of Eng 1060, or the Part B of Eng 1060. How can you pass, and perhaps even do well, in Part B of this subject? Well, the first thing I wanted to say is that Eng 1060 is brutally cumulative. And what I mean by that is, what you learn this week, you will need next week, and what you learn next week, you will need the week after. So you can't let a week slip by and then try and catch up. You will fall behind. So you do need to keep on top of things. Obviously, successful completion of Part B requires a good understanding of Part A, which is MATLAB. You need to know your MATLAB. You've got to understand the basics of programming before you can use programming to solve engineering problems. And I'm hoping that by now you probably all would have realized that the key to success in programming is to practice and practice and then practice again. It's the only way you can pick up programming. You can't do it by osmosis. You can't do it by reading and looking. You can only do it by doing it. So obviously you need to read the notes, watch the videos, attend the lectures, prepare for and do the labs. But really important, and this is particularly important in Part B, is to understand the concepts that we're going to go through. There's a lot of formulae in this part of the unit. Remembering these formulae is not really going to help you. And in actual fact, in an exam situation, these formulae will be made available to you in a set of pages at the end of the exam script. So you will have them. You won't need to remember them. However, understanding how to use them is going to help. You need to know what the formula mean, and you need to know how to use them. Knowing how they are derived and where they come from and what they mean is going to help a lot. And this is what I mean when I say try and understand the concepts, because if you understand the concepts, you'll then understand where things come from and how to use them properly. So it's really, really important in this part of the unit to understand the ideas. That's it for the introduction, so let's move on to the rest of the unit.